Hi, in this video, we are going to do chapter 4. We will learn about motion in 2 dimensions, particularly projectile motion. Projectile motion is the motion only under the force of gravity. So it could be a person diving in, or it could be some object thrown, so they usually follow parabolic curve. So we will learn about these things in this video. So let's start. Okay, so motion in the x and y directions are independent of each other. This is important. Even though the motion is in 2 dimensions, we can analyze the motion we can divide the motion into 2 as the motion in x direction and the motion in y direction. So we have a separate set of equations for each axis. So you can see it here. For x, we have this equation for the position, and for the velocity we have this equation, and we have another equation for initial and final velocities. So the first line is for the motion in the x direction, and the second line is for the motion in the y direction. You can see that these formulas are exactly the same, except they are written for x and y directions. So we solve problems in 2 dimensions by analyzing the vertical and horizontal motion separately. So the first case is the velocity is constant. That means the acceleration in the x direction and the acceleration in the y direction is basically 0. So that means constant velocity. So by the way, acceleration 0 doesn't mean the velocity is 0. So velocity can be some number, constant, in the case of 0 acceleration. So if the velocity is constant, that basically means the motion is along a straight line. So before moving into these images, so when you see an y-x graph, so you have to decide, you have to figure out if y is a vertical or is it just on the plane as well. So there are 2 possibilities. One of them is these x and y could be on the plane. So this could be, for example, it could be east direction, and this could be north direction, and these 2 axes are on the ground. The other option is this could be x direction, y direction, and y direction may be up, and x direction may be on the ground. So in this chapter, we will do examples regarding both. So let's look at this example. So this tortoise is walking with constant speed. Of course, it's not walking up into the air. So you can easily say that these 2 axes are on the ground. So this is on the plane. So if both x and y accelerations are 0, you can say that this tortoise will go in constant speed in this direction. So you can calculate the distance that it goes in 2 ways. The first way is you can basically find, if you know this distance, or if you know the velocity, which is constant. So velocity at any time will be equal to initial velocity because it's constant. If you multiply it by time, if you know the time, then you can calculate d. This is when you know the velocity. Of course, if you know the velocity, you can say what the speed is, so speed times time. The other option is, the second option, let's say you are not given the angle, or let's say you are given the angle, but you don't know, let's say you want to calculate the components, you want to go with the components, okay? Then what you can do is, or in the case, maybe you are not given the angle, but you are only given the components. That's also possible. So from the components, you can find the angle and you can find the velocity. That's one way. The other way is you can just directly use the component. So what you can do is you can find the distance that it goes in the x direction, which you will do x component of the initial velocity times t. As you can see, we don't have 1/2 ax t squared term. Why? Because ax is 0. It's given in here. So you can calculate x from this formula, and you can also calculate how much distance it goes in y. So you can calculate this as well. So this would be y equals this component, y component, v0y times t. Notice that I'm using the same t because t is common for both coordinates. There's no tx and ty. There's just one t. Okay, so when you calculate these two and x, now you can find the path d from the Pythagorean theorem, right? So this is d that you want to find. Now you know x, you know y. You can find d from Pythagorean theorem. So the point here is you can use the coordinates. You can use the motion in each coordinate separately, and then find the answer at the end. Or you can just find the distance directly from this formula as well. Of course, you will find exactly the same thing. Okay, let's move to projectile motion. So projectile motion refers to the motion of unpowered objects like a box, a stone. These are called projectiles, such as balls or stones, moving near the surface of the Earth under the influence of the Earth's gravity alone. This is important. So any object which doesn't have any motor or no parachutes or anything, it's just the object itself and no air resistance. Okay, if you just release it, and if the only force that acts on it is just the gravity, g, the only acceleration that acts on it, then we call it projectile motion, and it will follow a path which is parabolic. The word projectile is coming from project. It means to throw things. Sometimes you use projectors to throw the light sort of on the wall to watch a presentation or a movie. So projectile basically means throwing motion. In this example, a plane drops a cargo box. So drops means it drops it with zero initial velocity. It could throw it down as well. It could have some initial velocity in the down direction as well. That doesn't change the projectile motion. So as soon as this box leaves the plane, after that point, the only force on it is gravity because there's no parachute and we ignore the air resistance. Then we call this motion as projectile motion. So projectile motion has parabolic trajectory. Trajectory means the path that it follows. This function, if you write the function of this path, it will be a parabola. And remember, parabola are things like, for example, x squared. If you want to draw it, it will be something like this. So, and the velocity is not constant here. Now, if you look at the horizontal velocity, this velocity is actually the velocity of the plane, right? The same velocity. The box was going with the plane. So even after dropping it, it should have the same velocity, the box, because there's really if there's no air resistance, there's nothing in the horizontal that would change, no force, right? Is there any force pulling it back or forward? No. So that horizontal velocity, if there's no force, it will not change. If there's no force, there's no acceleration in the x direction. So this, you can see that it's 115, 115, 115. So it doesn't really change, right? But what happens and you can see that here, the acceleration in the x direction is 0 because there's really no force in the x direction. Now, what about the y direction? Well, there is gravity in the y direction, if there is acceleration, that means there is force. That also means the velocity or the y component of the velocity will change. So initially it's 0, y 0, y is 0. Why? Because the plane just dropped it. It could throw it down. It could have some initial velocity as well that wouldn't change the conclusion. So after some point, because of the gravity, see, the y component of the velocity is increasing. Here, it's even larger. Now, what happens to the velocity? Like not the components, but the total velocity. The velocity here is, the vector is in this way. Here, the vector is, if you know, because now it has both x and y components, now it becomes this way. And here, its angle is also changing, and magnitude is changing as well. So both the angle and the magnitude is changing. And as you can see from the figure, the magnitude of the velocity is increasing as well. Now, let's think about this green coordinate. Now, remember, you can put your coordinate system anywhere. You can put it down here, you can put it here, you can even put it like this. You know, you can choose x direction to the left, y direction down, either way, it's up to you. But in this case, I'm just choosing the coordinate system origin as this point. So I'm going to put the origin where the whole motion started, okay? So now let's analyze both the horizontal motion and the vertical motion. So the in horizontal motion here, in this case, it's x-axis, motion in the x-axis. So velocity, x component of the velocity at any time will be constant, right? And it will be equal to this. This is actually v0y, sorry. It will be v0x, which is 115 meter per second. Since there's no acceleration in the x direction, it will be always the same. So it will be constant. So this is going to be 115 meter per second. And what about x? What about the position? It will increase linearly with time. So again, there is no, so it will be velocity, x component of the velocity times time. And normally, you know, originally we have this part in this equation, but of course, because x acceleration in the x direction is 0, so we don't have this part. So here I wrote these t's in parentheses to emphasize that here vx and x are a function of time. In this case, of course, it's constant, but you don't have to write them. You can basically write x equals v0 sub x times t. That's fine as well, but you have to know that this changes with time, but initial velocity is constant. Now, what about the vertical motion? Motion in the y direction. Now, so if you remember the formula, it goes like this. This is time dependent one, initial position, which is not time dependent, plus initial velocity in the y direction. So y component of the initial velocity times time, 1/2 acceleration in the y component of the acceleration times t squared. Now, if I put my coordinate system here, this is the initial time. This is where the motion starts. Now, this is already origin, so there is no y0, right? So this is 0, as I mentioned here. Y0 is 0 since we put the origin of the coordinate system at where the box initially was. If you put your coordinate system here, though, then this y0 would be this height. But I'm not really choosing this. So that's actually why I put my coordinate system here, so that I don't have to deal with y0. Now, what about the initial velocity component in the y direction? Well, in this problem, it could be generally, it could be anything. The plane may throw it down or throw it even up. So it will go maybe up direction in some time and go down. That's also possible. But in this figure, the plane basically just drops in. So the y component of initial velocity is 0. So I will take this also to be 0. So what's left is only this part for the motion in the y direction. So now what is ay? Okay, it's going to be gravity. You already know it. So g is always down. Now the question is, am I going to take 9.8 or is it going to be negative 9.8? Well, you look at the coordinate system again. Up direction is defined to be positive, down direction is negative, so you have to take negative 9.8 meter per second squared for the acceleration in the y direction. And so this is the equation for position in the vertical direction. If you want to write an equation, write the formula for velocity in the y component of the velocity in the y direction, then you can also write it. It will be, so the velocity component, y component. So if you remember the equation, so there is usually a initial velocity, which in this case 0, plus acceleration in the y direction times t, and this will be so 9.8 negative 9.8 times t, and that will be the velocity, y component of the velocity, the formula for y component of the velocity. Okay, so as I mentioned, projectile motion is the motion where the object doesn't have any motors in it. It's not a helicopter that has a motor, or it doesn't have any parachutes. It's just something like a ball or stone or a box that goes in air under the influence of gravity only, and it doesn't have any parachutes or there's no air resistance. So that object thrown, it's called projectile. This object itself is called projectile. And the path that it follows, which I mentioned as parabolic, that path itself is called the trajectory. So for projectile motion, it doesn't have to start from the ground and end on the ground. It could be, for example, if you throw anything in this direction from anywhere or in any direction, let's say you throw a ball with 45 degrees with the horizontal in this direction. So it will start from here and it will go down like this to the ground. Again, this is also a projectile motion. You don't see the full parabola, but it still is part of the parabola. The path, the trajectory itself is part of the parabola. Okay, the acceleration is independent of the direction of the velocity. What does it mean? It basically means, let's say if you have an object that goes in this direction, the acceleration doesn't have to be in the same direction. So acceleration could be in this direction or in this direction, or maybe in opposite direction, a large magnitude. So it could be in any direction, okay? So in both cases below, so one case is you drop a ball or throw the ball down, and in this case, you throw it with some angle. So in both cases, the acceleration of the ball is only due to the gravity. Of course, after you throw it, not while you are still holding it, but after you throw it, after this point on, and after you throw it, the only force that acts on it is gravity, right? It's only gravity. So here, acceleration in the y direction is negative 9.8 meter per second squared, according to the coordinate systems shown in the image. So the point here is the acceleration, if you throw anything, let's say it starts from here, it goes up and follows this path and falls down here. During this motion, all the time, there is only one acceleration, which is in the down direction, and that acceleration is the acceleration of gravity. even though velocity is changing all the time, right? Velocity is in different direction throughout the motion, but acceleration is always the same. Even for the case where you throw something up and it goes down and then it goes up first and then down, throughout the whole motion, again, the acceleration is down and it's g. Okay, let's move to zero launch angle. The definition of launch angle, theta, is the angle of the initial velocity, it's this angle, with respect to the horizontal. This is the horizontal. So that's called launch angle. In this example, the launch angle is 0 because it's parallel to the horizontal. So if you have a motion with a 0 launch angle, then the trajectory would look like this. So it starts from here, and then it will follow this trajectory. And again, that trajectory, the function would be a parabola. Okay, let's think about these two situations where in the first one, so one of the guys, he just he is diving off an overhang into a lake. So diver one drops straight down. He is just dropping himself straight down. This is case one. And of course, he will, as he hits the surface of the water, he will have some velocity. And the second guy, he is going off with some launch angle. So he's going down, but he's also going in the positive x direction for some distance. The question is, so they have some velocities. So this is the velocity of hitting for the second guy for hitting the water. The question is, which one is greater? Is this velocity or this velocity? Which one is greater? Now, you can even see from the figure. So first of all, they will gain some velocities in the y direction. Now, what is the formula for that? It will be initial velocity is y component plus ay t. Now, for both of them, the initial velocity in the y direction is 0. Yes, the second guy has some initial velocity in the x direction, but now we are talking about only y. So both of them has 0 here. And for both of them, the acceleration is 9.8 and time is the same. So both of them are falling under the effect of gravity. So they will fall with the same, it will take for both of them the same amount of time to fall from here to here, t, and for this one as well, t. So then the final velocities for both of them will be the same. So final velocities, I'm talking about the y components of the final velocity. So this Vy and this Vy, they will be the same. But for the second guy, he also has the x component. It's actually the initial velocity in the x component, and it never changes because there is really no force in the x direction. But when you calculate the total final velocity, because of this x component as well, even though y's are the same, the final velocity will be longer than Vy. So we conclude that this second guy, he has more velocity splashdown, more splashdown speed when he hits the water than that of this first guy. Okay, we have another example which is actually similar to the previous one. In this case, instead of two guys diving off, we have one bullet, which is just released, so it's falling down on the ground. And we have a gun which fires the same bullet in this direction. So if this bullet is released, and at the same time, if this bullet is fired, then the time that it takes for both of them to fall to the ground is actually the same. Maybe this bullet goes in X direction, maybe let's say 300 meters. And let's say this height is maybe 10 centimeters. So it looks counterintuitive. This thing goes, the second bullet goes 300 meters, but in terms of Y motion, they actually fall to the ground at the same time. But that's true. This may sound counterintuitive, but the bullet fired with a gun horizontally and a bullet just dropped fall to the ground at the same time. The key ideas here are that the vertical motion in Y, so this falls down and this goes this way, but it has a component, if you think about it, it has a motion in X, if you think about the components, and it has a motion in Y. So the vertical motion and the horizontal motion are independent of each other. And the other key idea here is the flight time is the same for both when the launch angle is 0. So if you have a launch angle 0, like this, then the flight time for both of them, and when you release this, if you throw this down, it will be different. But if you release that, then the flight time for both of them will be the same. So it will fall down, they both will hit the ground at the same time. But if you had, so let's say you're firing this, so that means velocity, Y component is 0. But if you throw this with some initial velocity, then of course these times will be different. Or let's say you are releasing this bullet, but then you are firing this bullet in up direction, maybe with some angle, with the horizontal, so non-zero launch angle, then it will go up first and then come down like this. So in this case, also the t's, this t and that t here, they will be different t's. Okay, here is another example to zero launch angle. In this problem, a person skateboarding with constant speed, 1.3 meter per second, releases a ball from height 1.25 meters. So that's this. And the initial speed, 1.3 meter per second. So what is x? What is position at time equals 0.5 seconds? In other words, how much distance this person goes in half a second. So the coordinate system is already put here, so we will use this coordinate system. The origin is here, so that's x, that's y. To calculate the distance in x, we will look at this equation. Okay, now if you take this coordinate system, you can see that the initial position x0 is actually 0 with respect to this coordinate system, so this is gone. Okay, and is there any acceleration in the x direction? No, the gravity, there is only gravity, which is in down direction, and this person is not pushing the ball anymore. He's just releasing at this point. Okay, so then there's no acceleration in the x direction, so we will calculate, we will only take this part of the formula, v0x times t. So the initial velocity is 1.3 meter per second, multiplied by half a second. So what you get is 0.65 meters. Okay, let's move to the second part of the question. So in this part, it says, write the velocity at time equals 0.5 seconds in a vector form. Okay, so we already know the x component of the velocity, is, because there's no acceleration in the x direction, it will be always equal to the initial velocity, which is v0 x, which is 1.3 meter per second. Now, what about the velocity in y direction? So what I'm going to do is I'm going to use the second equation. Now, is there any velocity in this problem, initial velocity in the y direction? No. The ball is just released. So here it says, this is the key. Released means there is actually no initial velocity in the y direction. In principle, this person could throw it down. In that case, there will be some initial speed in the y direction, but in this particular problem, this is 0. So only the second part. And the second part, with respect to this coordinate system, the gravity, I have to take it to be negative 9.8 times t. So it will be negative 9.8 times t is 0.5 second. So from here, I find negative 4.9 meter per second. Now, if you want to write it in terms of a vector, so the vector would be something like this. First, I write the x component, which is here, 1.3. And I'm going to put x hat, which means 1.3 in the x direction. So let's say as 0.5 seconds passes and the ball is here, so it has some vx and also the y component. And so the total velocity is in this direction. So this is the vector velocity. And so I'm going to write now, let's write the negative sign here, negative for the y component, 4.9, and I have to put y hat, and it's in meter per second units. Now, if you look at the velocity here, its x component is in the positive direction, which makes sense because we got positive here. And the y component is in the negative direction, which again makes sense. It's in the negative direction. If you want, alternatively, you can also write this as, you can use the negative sign if you want here as well. So you can also write it like this. It will be the same thing. Okay, let's move to this example now. Now, in the previous examples, we had 0 launch angle, but here we are moving to general launch angles. So in this case, the dolphin will jump with certain angle, launch angle, theta. So the trainer drops the ball, this ball, and the dolphin jumps towards the ball. Now look at the dolphin. It's aiming exactly the ball, aiming at the ball while it's jumping at the same time. So that they do this thing, like releasing the ball and jumping at the same time. The dolphin will catch the ball in the air. So the dolphin, because the ball goes down like this, and the dolphin, even though it's aiming at, directly at the ball, of course, because of the gravity, it will follow this parabolic trajectory. So they will meet at this point. 4.10 is the whole height of the initial height of the ball. So now it says verify by calculations that the dolphin will catch the ball. The dolphin will catch the ball if x and y position of the dolphin and the x and y position of the ball will be the same at the same time. So if the time that it takes for the ball to come here at this meeting point and the time for the dolphin to come again at this meeting point, if those times are different, of course they will miss each other, right? So those times should be the same so that they can meet at this point. Okay, so we need the angle, we need this angle to find the x component and y component of the velocity of the dolphin. So v0x and v0y. The only way that I can calculate these is usually from, if I know the angle, so I can multiply the speed with a sine and cosine of those angles, that angle, so that I can find the components, x and y components. But in this problem, the angle is not given. But we can find the angle from the triangle. Now look at the problem. We have a triangle here, which actually helps us to find the angle here. That's theta. So the triangle is like this. This is the theta. So this is 4.1, and this distance is 5.5. You can see it from here. Now, if you calculate the tangent, it will be 4.1 divided by 5.5. Now, to be able to find theta, now theta equals inverse tangent of this number, and the calculator will give you 36.7 degrees. So now we have found the angle. We can calculate the components of the dolphin's velocity, those components, x component and y component. For the x component, I have to multiply 12 by cosine of that angle here. And for the y component, I have to multiply 12 by the sine of that angle. So in the following calculations, we're going to use these components. So I'm going to carry these to the next slide. Let's move on. So these are the components of the velocity of the dolphin. So now that the ball and the dolphin meet at point B, let's call this point B. That means that both the ball and the dolphin take exactly the same time to get to the point B, something that I mentioned in the previous slide. So if we knew the height at point B, if I can find this height, then if we knew that height, we could calculate the time that it will take for the ball to fall until the point B, or the dolphin get to the point B. So if I knew, let's say 2 meters, if it was 2 meters, then the rest will be 2.1 meters. I could easily calculate the time for the ball to fall down for 2.1 meters. So I could find the time. But that doesn't work here because I don't really know what this height is. Okay, I have to use some other ways to solve this problem. But we don't know that height, as I mentioned, so we can calculate the time that way. We cannot really calculate it because we don't know that height, the height of B. However, we can calculate the time from the horizontal motion of the dolphin. Okay, so we can actually calculate the time from here, and this component, V0x, which is given here, 9.662. Now, I know the velocity, I know the x component of the velocity. I know the distance, then I can find time, right? So I'm just going to use this one. Notice that there is no acceleration term, like 1/2 axt, because in the x direction, there is no gravity, there's no force or anything. So it's motion with constant speed. So I have to use only this part of the equation. Okay, so if you want to find t, divide both sides with this velocity, and the formula for t will be d divided by x component of the velocity. And because I know d, I know the x component, which I calculated in the previous slide. So you can easily find time from here. So the answer is the meeting time, the time that it takes for the ball to fall down to point B, which is also the time that for the dolphin to reach to the point B, is this time. So it takes about 1/2 a second. So in this case, I actually calculated this from the dolphin's motion, dolphin's horizontal motion, but I haven't showed you that it really takes the same amount of time for the ball to fall down. So I have to show you also that the time for the ball to fall down here is exactly this time. If it is, then we can say, yes, these two objects, the dolphin and the ball, they will meet at point B. Let's do that now. So the dolphin will be at point B at time equals 0.572 seconds. The dolphin will catch the ball only if the ball will also be at point B at the same time. Now for the ball, I'm going to use this formula. Okay, so the position for the ball. Now calculate the height of the dolphin at this time. Now how do you calculate this height? Now in the previous slide, I calculated the time. So I know the time for the dolphin, and I know the initial y component of the initial velocity, which is, I actually calculated it, it's here. Okay, so I know the initial position for the dolphin. I know its initial velocity in the y direction. I know acceleration is gravity. I know time, which I calculated, which is here. So from all of these information, I can find y. And y will be the height of the dolphin, which is actually this height. This height. I can call it y dolphin. I can calculate it from this formula. So the height of the dolphin at this time will be the initial position of the dolphin with respect to this coordinate system. See, the origin is here. The dolphin is initially at the origin, so it will be 0. So this is 0. You can see it here. The initial y component of the initial velocity is 7.17, which is here. And the time for the dolphin to reach to the point B, we calculated it. It's this one. Acceleration, it's negative 9.81. The reason is it's negative because the up direction is positive, down direction is negative, so that's why it's negative. You may be wondering why we are taking 9.81. Doesn't matter, it's up to you. You can, usually it's given in the problem if you should take 9.8 or 9.81. So if you take 9.81, of course, it's going to be a little bit more precise. And then the time squared. So if you do this calculation, you will find the height of the dolphin is 2.5 meters. Okay, let's calculate the height of the ball at the same time. If the height of the ball is the same, which is 2.5, then we can say that for this time, they will be at the same height. That means they will meet at point B. So for the ball, now what is the initial? So this, now it's not 0 anymore. So this formula is actually for the ball and for the dolphin, for both. So here we do dolphin. Here we use the same formula for the ball. Now the initial height for the ball is 4.1. It's not 0. Why? The origin is now on the ground, so it has some initial height. See, this initial height is, it's given in the problem, 4.1. 4.1. So that's why y0 is 4.1. Okay, for the ball, does it have any initial velocity in the y direction? No, it's just released, so that's 0. And then we use the gravity at the same time, and what we find is the position of the ball. It's not the distance that the ball goes. Remember, these formulas, they give you the position, not the distance traveled. So the position of the ball is 2.5. That means the ball is at 2.5 at this point. So now you can compare these two. As you can see, they are the same. So from this, so for the same time, they are at the same position, and that means they are going to meet at point B. So in this exercise, we proved by calculations that the dolphin and the ball, they will meet at the same point. Now, I have two conceptual remarks. They are actually interesting. So imagine the case the gravity is 0. So if there were no gravity, what would happen if you release the ball? Well, the ball wouldn't fall, right? It will just stay here. And the dolphin's trajectory will be straight line. If the dolphin aims at this direction, if that's the initial velocity, and if there's no gravity that will pull it down, the dolphin actually, it will go straight, right? It will go, and because the ball is not falling down, because there's no gravity, so they would meet at this point A. So the dolphin would catch the ball at point A. Now, since there's gravity in reality, and it affects the ball and the dolphin at the same way, they lose the same amount of altitude, the distance from A to B. So you can imagine that in the case of zero gravity, the dolphin would reach here, but because of the gravity, the dolphin loses some altitude and end up here. And that's the same for the ball. The ball will be staying here with zero gravity, and because of the gravity, it's losing some altitude, which is exactly this much again, this much. So they lose the same amount of altitude, the distance from A to B, which again makes the dolphin catch the ball. So it's interesting, as long as the dolphin, so I'll say it in the next slide. So as long as there are two conditions, the first condition is the dolphin aims at the ball. So the dolphin aims at the ball. And the second condition, the dolphin jumps right when the ball is released. So they start the motion at the same time. The conclusion is, if these two conditions are satisfied, then the dolphin will always catch the ball regardless of its initial speed. That's interesting. So it doesn't have to be 12. It can be any speed. So any speed, as long as, of course, within some bound. If it's extremely too slow, then the ball, of course, will fall down and it will not be able to catch it. But for a certain number of speeds, the dolphin will always catch the ball as long as these two conditions are satisfied. For example, if the dolphin's initial speed is greater than 12, let's say it's 20, it catches the ball somewhere above B. So if the speed is more, so that would mean it would actually follow this trajectory, something like this, because the speed is more. So it will end up here. And because it has more velocity, it will come here quicker. So the ball will fall down. Also, it will take less time for the ball to fall down this less distance. So they would again meet at this point somewhere above B. If the initial speed is smaller than 12, then still it catches the ball, and it will catch the ball somewhere below B. So if the speed is, let's say, less, let's say maybe this much. So in this case, you can see that the x component is smaller than the x component of the original velocity. So if you have smaller x component, that it means it will take more time for the dolphin to reach to this line. So it will follow a path like this. So it takes more time to come to this point because the x component, velocity of the x component is smaller. So x equals vxt, right? So x is fixed. This is 550. If x component of the velocity is smaller, that means time is larger, so it will take more time. And for the ball to fall from here to here, it would take, again, more time. So it turns out that they will again meet at some point, but of course below B. So this is interesting as long as these two conditions are satisfied. If you change the gravity, if you change the initial velocity of the dolphin, nothing changes. In each cases, the dolphin catches the ball. Okay, so now let's talk about symmetries. In physics, symmetry means similarities. So notice the symmetry in the velocities throughout the motion. Now, let's say if the velocity here is like this, so it has certain angle and certain x and y components. The velocity, if you go to the here, so just go to the parallel point here, this is the trajectory that it will follow. At this point, the x component will be the same in the same direction. Now, the y component of the velocity, the magnitude will be the same, but it will take a negative sign because now it's going down. So then the angle will be the same, except it will be the negative angle, but the magnitude, if it's 30 degrees here, it will be 30 degrees here as well. And the velocity will be like this. So basically, you can see that the magnitudes of the velocities are the same, except the direction changes, and the direction doesn't change arbitrarily. If it's theta with the horizontal here, it will be negative theta with the horizontal here. So in a problem, if you are given the velocity at some point, let's say here, and if the problem is asking what is the velocity at this point, you don't have to make lengthy calculations. You can just say x component will be the same. Why is it the same? Because there's no acceleration in the x direction, so it will not change. Y component will be the magnitude at the same level, will be the same, except it will be negative because it will be down. So from this triangle, again, you can calculate the velocity. The magnitudes will be the same. Same thing here. So if the velocity is here like this, at the same level here, it will be like this. And if, let's say, if it takes 5 seconds to go from here to here, this height, so let's say A, B, if it takes 5 seconds, let's say 5 seconds to go from A to B, from here, D, let's say this point D, say this point E. So from D to E, it will again take 5 seconds. If it takes 20 seconds from the origin to the top, then again, it will take 20 seconds from top to the ground. So the same thing. If the question asks, let's say, what is the final velocity, then you can actually find it from, so the velocity here, v, will be exactly as the velocity, the initial velocity. So this one, in terms of magnitudes and angles, of course, they have different directions, but let's say this angle is alpha. This angle will be also alpha. And the speeds, so the magnitudes of the velocities, they will be the same as well. Okay, so related to that, let's do this example. 2 snowballs are thrown with the same speed, but at positive 40 degrees and negative 40 degrees. So which one is true? So one of them is thrown this way with velocity, with speed v. The other one is thrown with negative 40 degrees this way with speed, again, the same speed. So they're going to land on A and B. So landing speed A is landing speed greater than landing speed of B, or equal or smaller. So which one is true? Now, if you look at this one, from what we learned from symmetries, so at this point, it goes off with velocity v. Okay, so it will come here, and it will have exactly the same speed at this point, except instead of 40 degrees, it will have negative 40 degrees like this, right? So this is negative 40 degrees. Here we have negative 40 degrees. Okay, now if you look at the motion after this point, now look at the motion here. forget about the motion here. Now, they have the same angle. They come out with the same angle. And they have the same speeds. Then they will fall down. Their final velocities, V final, will be exactly the same. So the correct answer is 3. Now, you may say, do they fall at the same time? No. The reason is, so this one, A, it actually goes down like this. So let's say if it takes T, TA, for this one, yes, from here to down here, it will take, let's say, again, the amount of TA, but there is an extra motion for B. Let me call it T. So for the time for A, maybe I should use T1. Let me call this T1 and T2. For A, it's only T1. For B, it's T1 plus T2. So it takes more time for B to go down. But as far as we are concerned with this, with the landing speeds, the landing speeds will be the same for both. V final, V final. So what I used here for the landing speeds to find them to be equal to each other, I actually used symmetries that I introduced, that I mentioned in the previous slide. Okay, now let's talk about range. Range is basically, it is the horizontal distance for a projectile, the horizontal distance a projectile travels. So if you have a trajectory like this, range will be this. If you throw something from the top of the building, let's say this way, and it will go like this. So in this case, range will be this distance. So it's basically the horizontal distance that a projectile travels. Can we find a formula from the ones that we learned before, a particular formula for range? The answer is yes. The formula for the range is this one. You can directly use this one if the question is only asking the range, but not the height or the velocities or the time. So how do you derive this? Let me show you. First, you start with this one. So in the x direction, the motion is governed by this formula, right? There's no acceleration in the x direction. So the range is the distance. So I'm going to write r instead of x. And what is the velocity in this direction? It's actually v0, the speed, times cosine theta. So v0 cosine theta and multiplied by time. So this is one formula for the range. The problem here is there is t, but for the range, I wanted to depend only on the initial speed, the gravity, acceleration of gravity, and the theta angle. So I don't want t, so I have to get rid of that t. To be able to do that, I'm going to write another equation. This time, I'm going to write the position equation for the vertical motion. So I can use this position. So I'm going to find t from here. So for the final position, I can take, for example, the top point. So I can use this equation from origin to the top point. But for that, I have to know the height, right? For y, I have to write the height, but I don't know height. The height is not given. So what can I do? What I can do is, instead of taking the position for this formula, for taking the time or the motion from origin to the top, I can actually take the motion, the whole motion from origin to the point that it hits the ground. Now, why do I do this? Because it actually gives me the final position in y as 0, right? That's good. That's something I know. I don't know height, but I know the final position in the vertical will be 0. So I'm going to use these 2 points and apply this formula. So initial position is 0 because it starts from origin. Final position is 0 because it hits the ground, final position in y. Now, what about the initial velocity, y component of the initial velocity? I have to calculate it from v0 times, so that angle is sine theta, so it's here. And I'm going to multiply it by t, and as for the acceleration in the y direction, I will use negative g, which is negative 9.8, times t squared. Now, so these parts are 0, so that's, you can easily solve this. Now you can write it as, take this second part to the other side of the equation. So you will have 1/2 g t squared. And on the right-hand side, we are going to have v0 sine theta t. So let's cancel this t with this power of 2. And I'm going to divide both sides with g. So this g is gone from here, so it comes here. And this 2, I'm going to take it to the other side in the numerator, so that's gone too. So that's the formula for t, 2v0 sine theta divided by g, which is here. Now, I'm going to use this formula for t and substitute it in the first equation here. So for the range, if I do that, for the range, what I'm going to get is, so there's going to be 2, there's going to be v0 squared, because there are 2 of them, and there's going to be cosine, there's going to be sine divided by g. Now, you can use this identity. This is from trigonometry, it has nothing to do with physics. So if you have 2 sine theta, which is coming, sine theta is coming from here, cosine theta is here, you're calculating r, and there's also 2 here. So 2 sine theta, cosine theta, you can write it as 2 sine 2 theta. And if you also use this, the final equation for range, without depending on time, is given by this. Now there's one caution here. This formula for r works only if the initial and final elevation are the same. So the projectile launches and lands at the same level. Why? Because if you remember, while deriving this equation, this formula, I actually calculated the initial position and final position to be on the ground. So use this formula for the cases where the initial height and the final height, or the positions in vertical, are the same. So you can use this formula for that case. Okay, so we found range is initial velocity squared divided by g. This is g, which is always a positive number. Okay, 9.8. It never becomes negative here because it's just a value. You cannot have negative distances, negative ranges. And sine 2 theta. So this theta is the angle. So let's say if the angle is 30 degrees, so it goes like this. This is the ground. And let's say you want to calculate r. So here you would write 30 degrees. But ultimately, because it's multiplied by 2, you would be calculating sine 60. Okay, so let's find the maximum of range. So the question is, at which angle, 30 degrees, 40 degrees, 50 degrees, 60 degrees, what is the maximum, what is the angle that would give me the maximum range? Okay, if you look at here, if you throw it 30, it reaches maybe around 35. If you throw it with 60 degrees, it reaches again the same point. But if you throw it 45 degrees, it reaches further away, right? And by the way, air resistance is always ignored unless you are told that there is air resistance, so we ignore it. So the question here is, what is the angle that would give me the maximum range? In this case, 45 gives maximum range more than 60 and 30, but is it really the angle? Let's calculate it. So this is the range. So I want to calculate the maximum value of this definition. So v0, it's initial velocity, so we don't change it. It's given. So you throw something with initial velocity, certain initial velocity. G is given. So the only thing that I can change here, angle. Of course, you can also change the initial velocity, but imagine that you are already throwing in it. You're using all of your power to with the maximum initial velocity. So, but still, I can play with the angle. I can change the angle. So now, if you want to get the maximum of r, you have to get the maximum of sine 2 theta. When is it maximum? Now, you have to remember that the sine function always gives you some number between -1 and +1. So even if you write, sine 1 million, let's say 1 million, it will be again some number between 1 and -1. Okay, so that if I ask you what is the maximum of sine function, then it's 1, right? So when does sine 2 theta becomes maximum? Well, it becomes maximum when this angle is 90 degrees. This 2 theta is 90 degrees. When does it become 90 degrees? Well, it becomes 90 degrees only if I take theta to be 45. So the answer is 45 degrees. If you have 45 degrees, you get this. This becomes maximum. It becomes 1. Okay? So you get the maximum range. It's actually shown in green here. Any other angle, for example, if you throw it with 10, it will maybe go here. If you throw it with 80, it will maybe go all the way up, but then fall down here. So, but the maximum occurs at 45 degrees. What happens if I choose another angle? Let's say I choose 30 degrees. Well, sine 230, or let me choose 15 degrees. Sine 215, so 2 times 15 is 30 degrees. Sine 30 is 0.5, so it's less than 1. Any other angle, take, for example, even you can take 90 degrees. So if you take 90, 2 times 90 is 180. What is sine 180? It's 0. That makes sense because the range becomes 0 because now you are throwing it at 90 degrees. It will go up and go down at 0. So 45 degrees gives you the maximum range. And the maximum range, because sine 2 theta, sine 90 becomes 1, you can write it like this, the maximum range. So this is from the previous lecture, this plot. If you have no air resistance, then you get parabolic curves like these. So if you ignore the resistance and if you have something like a hard ball, a cannonball type of thing, the air resistance will be small, even though air resistance in reality is not 0, but if you have something like a cannonball, which is round and heavy, then the trajectories will be very, very similar to parabola. But if you use some wadded up paper like this, you can actually make this experiment easily. Do this right after this lecture. So have some wadded up paper, but don't squeeze it too much. Make it loose, and throw it with some angle, and you will see that it will follow something like a parabola, but then it will kind of fall down more in a more steep path. So this is real life when you have air resistance, and if the object has, if it's light and if its shape is not concentrated, not squeezed, a lot of air will go in, and it will feel a lot of air resistance. This is real physics, which you can try at home. But again, if you have something like a cannonball really hard and the surface is smooth, then the trajectory will almost look like these parabola. So that's all for chapter 4.